Welcome everybody in the lecture hall. Welcome everybody on Zoom. Welcome everybody watching us from the future. I have a few slides to finish from the relational model. Before I do that, I like to ask a few questions on the Clicker app that maybe you can answer just to check that you've been following. So here's the first one. What is a relational table? Is it a mathematical relation over atomic attribute domains? Is it a mathematical relation over several sets of attributes? Is it a set of relations between strings and values with monotonous support? Or is it a set of maps from strings to values and that additionally fulfills relational integrity, atomic integrity, and domain integrity? All right, so we have a majority here. And the majority is correct, but in fact, there are two possible definitions, if you remember. The one that I really like, and that's the one that you answered in a majority, is a set of maps, right? Every map maps the attributes to the values. But we need to add on top of that these three rules that I told you about: relational integrity, atomic integrity, and domain integrity, right? So this is the one that I really like because it's also big data compatible. So later we can generalize to other kinds of databases. And the other one is a mathematical relation over atomic attribute domains. And this is indeed the textbook definition and the reason why this is called a relational table or relational database. A mathematical relation over several sets of attributes that's made up, right? So if you would have a relation between sets of attributes, the only thing you would be relating to each other are the attributes themselves, but there's no values in there. So this is why this definition is incorrect. And then the other one is also totally made up, relations between strings and values with monotonous support. It's not just relations, it's maps. It's a special kind of relation between strings and values. All right, but just so that, again, two definitions: as a relation or as a set of maps. And we'll use a lot the set of maps in this lecture. Okay. And I have this other one. We have covered these three integrity constraints. I realize the question is a bit stupid because the answer was kind of the previous one. But anyway, which one of these is not one that we covered? It never hurts to repeat, right? When you learn, if you repeat, and repeat in spaced repetition, then this is how your brain is eventually remembering all of that. Okay. Let's take a look. And yes, indeed, that's the attribute integrity, right? So this is the one we didn't talk about, and it actually doesn't exist. That's also totally made up. There is no reason why the attributes, so that's the names of the columns, right? There's no reason why they have to have the same length. All right, and the other three are indeed the three fundamental constraints that we have on a table. So let me go back to the very few slides that I have left, because we almost finished actually last time. So I'm going to repeat. Who uses Duolingo? So learn languages. It's a bit the same principle, right? In Duolingo, it just shows you the same words with a space of 1 week, and so that your brain recollects. And so I like to repeat things 1 week to the next so that it really is remembered. So The approach has a set of maps. So you can basically look at set of maps. There's one problem with that, is that it can produce things that are not tables, because sets of maps don't need to all have the same support, right? So you need a set of maps, but you need to add these three on top to really make sure that it's a table, right? Relational integrity, same support for all maps. Domain integrity, every column has values in the same domain. And atomic integrity, meaning that the domains are atomic, so the values are all atomic, right? Then you have a second definition if you want to allow for repeated entries, repeated records in a table, which is kind of fine. I mean, when you actually compute things on the fly with your tables, you want to allow for that. And so in that case, you just change the definition to have a bag of maps. So in that case, you would have three maps, but two of them are repeated, right? The first and the third one are the same. So if you want the bag semantics, then this is fine, you allow that. But again, you need to add the three constraints always, right, on top of that. So it's a bag of maps with these three constraints. It's same support, atomic values, and domains in every column. But the difference with the set of maps approach is, again, that you can repeat records, right? So mathematically, you have this ugly formula on the top. What it's really doing is just it's associating every record with the number of times that it appears. It's really that simple. It's a function from records to from maps to integers, right? You don't need to worry too much about that. The one thing you need to remember is just that in the bag semantics, we allow for duplicate records. That's just it. Okay. And finally, the third one, which is the set bag and list. Yes. So the list semantics, it's the list of maps, and then you basically care about the order. So it's not the same thing, 1, 2, 3 or 2, 3, 1. These are not considered the same tables with that semantic. And then you have an even uglier formula there that is basically just assigning positions to maps. That's really just saying the first map is this one, the second map is this one, the third map is this one for some value of n, which is the length of the table. But again, you need to throw in these three always on top of that. So it's really easy, set of maps, bag of maps, or list of maps, depending which one you want, plus the three constraints, okay? Now, because we have these constraints, in particular, relational integrity, it means that we always have the same columns everywhere. All the maps have the same support. In that case, it's PID, last, first, and country, PID. This is called the schema, in fact, when we start looking at this. So the schema contains the names of the attributes, which are the same for all maps because of relational integrity. Second, every one of these attributes is associated with a domain or a type, which is the kind of values that are in there. PID is an integer, last is a string, first is a string, country is a string. That's because we have domain integrity that we can do that. So we can assign domains to every column. And finally, atomic integrity means that the domains we have here are all atomic domains, integer, string, data, and so on. We will not have as a domain, for example, table, because we don't have a table in a table in a table. So what you will find a lot, what people do, especially in textbooks, is that the schema of a table, visually it looks like this, right? Where I have the names of the attributes here, and then I have the domains here, then the data. What people do is that they give a name to the table. For example, this table could be called scientists, and then they list the columns. So you have PID integer, last colon string, first colon string, and country colon string, right? So this is the schema of the table that says what the attributes are and what the associated types are. This will cover later. The underline just means it's the primary key. It's like the social security number for people, right? That's what uniquely identify records. But again, I'll come back to that in a couple of weeks in database design theory. For whom is that clear? Right? And this is what we'll focus on now with SQL. We are going to see how in SQL we can create tables by giving this right here. Now, we've done a lot of math for that. This is the theory. It's actually very important because then when we study the relational algebra, you will see that we will have theorems that some of the operators are commutative, associative, distributive, and so on. So there's a lot of nice properties. We can only do that kind of theorems if we have math, right? So if you really focus on the math and only the math, then you're going to get that thing on the bottom that is a purely mathematical thing that is really literally a relation as a set of maps. So it's a map, it's a map, it's a map, it's a map, right? In a map, you have this notation to say that you associate this to this, right? It's the for every function. So basically, it's a set of maps, but this is very ugly, right? And then it belongs to the set. It's a subset, sorry, of the set of all maps. This is very ugly. Who agrees? You would never draw a table like that, right? And in fact, yes, indeed, database people never do that. This is really just for the math behind. What database people look at is this. It's so much simpler. And again, it's thousands of years old, so everybody understands that. And in this lecture, we will mostly focus on this. We'll just care about the math when we do a bit of theory and write a few formulas. But the good news is that a lot of the math is actually very visual. So of course, you can write down the formulas and so on. But since it's very visual, it makes it a bit intuitive to understand what's actually going on, right? So you won't have to worry too much about the math. Okay. Now, in terms of notation, especially in database design theory, what people do is that when you have a record here, which we tend to denote as T for tuple, because again, record, tuple, row, it's all the same thing. So we call it T. T is really the whole record, the whole row. And then that would correspond to this map, right? This record here corresponds to this map. And then you write T dot customer ID, T dot security ID, T dot quantity. It's a bit like object-oriented programming, but you can also put it as a subscript, right? So the name of the attribute. So T customer ID is 1, T security ID is is in, and quantity is here 135. Okay. All right. For whom is that clear? Very good. So that's basically it. Now you master the whole thing. And when you have a database is just a set of tables. You can have 10 tables, 20 tables, 100 tables in your database. And every one of these tables is a set of maps that satisfies the 3 rules, or a bag or a list of maps if you want to allow for duplicates and for order, right? So now I probably repeated it 10 times, but hopefully now it's very clear. So I'm done technically with the relational model. Do you have any questions so far regarding this? Anything that is unclear that you want me to explain again? No, it's all good. On Zoom, anybody? Last chance to ask questions. Doesn't seem like this, right? Doesn't seem like there's any questions on Zoom. Okay, then I'm going to stop the recording here.